let's recall the Laplace transform is defined in the following way. It's supposed to be a fancy L. This is supposed to be a curly bracket, but really you can put whatever you want. The Laplace transform of some function of time is defined as the integral from 0 to infinity of that function f, and I'll omit writing the of t, times, actually I will not, of t, times e to the minus st dt. And as well, we know that f has to be of exponential order, which means that the magnitude t has to be less than or equal to m e to the ct for, big T, for some constants m and t greater than 0, and some constant c as necessary. So this just means f has to be a function where we can come up with another exponential specifically that at some point in time is bigger than f forever after. So for example, if we have f, let this be 0, we have f as like, it goes up, like it has a spike here, and it goes up 10 billion, but then it comes down, and then it kind of just goes up linearly here. Well, even though this part over here is 10 billion, if we choose our big T to be after this point, say this is 5 seconds, well, clearly an exponential is going to grow faster. So this function, whatever it is of exponential order. That's all we mean. So if f is of exponential order, then the Laplace transform is defined like that. So let's check the linearity of the Laplace transform first. So linear operator is useful because of two facts. For one, if it acts on a scalar and whatever you're operating on, then what you're going to get is that scalar comes out, same thing. And two, if the function acts on a sum, then what you're going to get is it can be broken up into f of x plus f of x. So an example of this we know would be the derivative operator, would be the integral operator, we know it does that, would be the Laplace transform, right? So let's show that this is true for the Laplace transform. So what we have to do is check that a scalar can come out and check that the summation can be broken up. So with this as our definition of the Laplace transform, let's just copy this over. So if this is the Laplace transform of f, let's just make an adjustment. Let's say k of f. Right? So this is the Laplace transform of k of f of t. So in fact, let me write this. Laplace transform of k, where k is just some scalar, doesn't matter, is equal to this. Well, we know by the properties of integrals, since k is a constant, this right here is just the same thing as bringing k out, which of course is just the same thing as k times the Laplace transform of f of t. Now, as we move on, I'm gonna omit writing the of t over and over again, but I'll let you know when that happens. And actually it's gonna happen now, so we proved the first one, that it is invariant with respect to a scalar, or in other words, the scalar comes out. Now the second one is just that it distributes over the sum. So here's where I'm going to start omitting the of t because it gets tedious. But of course, if you want to be careful, you always include what variable it is with respect to. Well, this is going to be the same thing up here, but we're just going to put this as our function. So this is going to be equal to the integral from 0 to infinity of f plus g e to the minus st dt. Well, we know our rules of multiplication, so this is just going to be the integral from 0 to infinity of f e to the minus st plus g e to the minus st. Again, keep in mind that these are of t and of t, f of t and g of t. I'm just omitting writing the of t. And of course, we know that the integral is a linear operator. So the integral of a sum is the sum of integrals. So we can say that this is the same thing as integral of f e minus t. Now don't forget it needs its own dt, that it's its own integral, plus, and then the integral 0 to infinity of g e to the minus st. But if we recall right up here from the definition of the Laplace transform, this is the same thing as the Laplace transform of f plus the Laplace transform of g. Right, and if it's unclear what I'm trying to do, this fancy L kind of supposed to be written like that or that. You just write L. Nobody will judge you if you just write L. Just as long as it looks like an L, it's clear. I, however, am writing fast. So that's going to be linearity. And this essentially proves it, because those are the two conditions that you need. One, that the scalar comes out, and two, that addition is distributed. And we've shown that. Are done here. Now, I want to motivate taking the Laplace transform of a derivative. So we're familiar with some of the basic Laplace transforms, but I want to motivate taking the Laplace transform of a derivative for solving equations that look like this, with initial conditions. Now the initial conditions are very important, and you'll see why. But the initial conditions, and as a hint for the future, actually play into the Laplace transform. It becomes part of it. And specifically, initial conditions at 0. Steady state conditions are when the initial condition at 0 is 0. But in general, the Laplace transform is very, very reliant on initial conditions at 0. Now that does not mean that this here has to be 0. This can be anything. But this must be true. So normally we could solve this in a bunch of different ways. This is separable. This is, we can solve this as a constant coefficient equation. If you have some other method, you can solve it as a series. You can use Frobenius's method, my favorite Frobenius method. But we're going to try solving this via Laplace transform. So what we can do is we can take the Laplace transform of both sides, manipulate the equation, and then take the inverse Laplace transform if it's convenient. So let's try it. Let's take the Laplace transform of this side, y prime plus y. Oops, so let's make that a little neater. Right. Is equal to, what's the Laplace transform of 0? Well, if we plug in 0 right here, it just becomes 0 times e, so it's 0, and the integral of 0 is 0, plus a constant, but remember we have a definite integral, so it's just 0, 0. Now, this distributes, right, because it's a linear operator. It's going to be y prime plus here, y. What is 0? Trouble, we don't know what this is, right? Well, we don't know yet. So let's use that as a motivation to find out what the Laplace transform is. So let's go ahead and define, that's not a straight line in the slightest. Let's go ahead and define the Laplace transform of y to be big Y of s. All this means is this is some mystery Laplace domain or S domain function. We don't know. And it may be unsatisfying to define one unknown in terms of another unknown, but just like in a differential equation where we can manipulate algebraically, this is going to give us the ability to manipulate algebraically in the S domain where we might come to a better solution. Well, I wouldn't be doing it if we would come to a better solution, but you have to take a small leap of faith. So based on this, let's apply the Laplace transform by definition to y prime and see what we get. Well, we know the Laplace transform of y prime is defined as the antiderivative, the integral from 0 to infinity y prime to the minus st dt. Now notice y prime is probably a function of x. It doesn't have to be. Just be careful that whatever comes in here, this has to be the same as this. So if you're working dx, this is dx. If you're working d smiley, this is d smiley. I'm just using t because we don't lose any meaning here. We're all in understanding that I just mean whatever variable y is. So if it was of x, you could change it to x. I'll keep them in t for sake of continuity, but do be careful when you're playing fast and loose with notation. All right? So y prime times e to the minus st. Well, if we look, first of all, this is a product, right? So this immediately screams integration by parts. But another reason you may want to do integration by parts is that we already know what the integral of y prime is, and the derivative of e is an extremely simple thing to calculate. So let's recall our formula for integration by parts. And if you remember it differently, I apologize, but this is how I remember it. So we're going to plug in our bounds. If we have u dv, always going to be equal to, well, not always, but in this case, uv evaluated at our bounds. This is an important step, minus the integral from 0 to infinity, or our bounds in particular, of v du. Right? So that's what we're going to be using. So in this case, obviously, it's convenient to make this our dv because we know what the antiderivative is. It's going to be y. Right? So let's write that out. The integral of this is going to be u times v. So our u is going to be e to the minus st. So e to the minus st times our v. Our v is just going to be the integral of y prime dt, which is just y. So y. And now here it's important to put back the t, and you'll see in a moment why. Evaluated from infinity to 0, minus now the integral from 0 to infinity of v du. So v is, again, just going to be y. Du, well, the derivative of e to the minus st is just going to be minus s. So I'll take this minus s out and I'll put it up here. E to the minus st. dt, never forget the dt. So two things have occurred that you may see. First of all, I feel like this is about to give us our initial condition. And two, this looks like this, right? And if you take a moment and expand this out by definition, that's what this is. So what if we just derived that? Let's evaluate this. If we plug in infinity, remember fundamental theorem of calculus, we don't actually plug in infinity, but we can take that leap. E to the minus infinity is going to approach 0, as e to the minus b is going to approach 0 as b approaches infinity is the most formal way I'm going to say it. So that value is 0, and then if we plug in 0, e to the 0 is always 1, and we can plug in y of 0 right here. So we'll have minus y of 0. The reason it's minus is because fundamental theorem of calculus is plug this in minus plug this in. So minus y of 0 plus now s stays as is. Remember, s is a constant with respect to t, so it can come out. And now we know what this is. This is the Laplace transform of y, so this is going to be our y of s. And we're done, right? That is the Laplace transform of the derivative. Notice the Laplace transform has taken the operation of derivation and it is now transformed into multiplication. Right? Multiplication and translation, yes, but essentially multiplication. So this has made our problem of derivatives, so solving a functional equation, like solving for a function with derivatives, instead it has turned it to solving a functional equation with some factors, which is much, much easier, and we can do it algebraically. And again, to prove it, or to prove that it's easier, well, I can't prove that it's easier, but I can demonstrate it. Let's try solving that problem from earlier. So we have y prime plus y, that's a big Y, plus y equals 0. Well, let's just inspect what our solution is probably going to be. Take a moment, see by any method you want to do, and confirm that our solution is going to look like e to the minus x. So this constant can be anything, just as long as we have e to the minus x over here. Why? Because when we take the derivative of e to the minus x, it's going to come down and give us minus e to the minus x. So long as these two constants are the same, except for a minus sign, they're always going to add to 0. That's our solution. So fine, we got that by inspection, but for the point of demonstration, let's come back to the problem. So we had it right over here. Let's copy this over. Right here. But this time, we don't need to worry about this previous question mark, right? We know exactly what the Laplace transform of a derivative is. Let's plug it in. We have y of 0 minus y of 0, always keep in mind your signs, plus s, y of s, plus, again, y of s is equal to 0, right? So, well, we know this goes to 0 immediately because of our initial condition here, y of 0 equals 0. So what we're left with is sys plus ys. So we can factor out a ys, and we'll get s plus 1 is equal to 0. All right. My apologies. I just realized with our initial conditions, this is actually quite a boring problem, because if we divide both sides by s plus 1, we get the solution that, of course, y equals 0. So let's make a small edit to our problem, and let's say that y of 0 is not equal to 0, y of 0 is equal to 1. Right. This should make our problem a little bit more interesting. Yes, in case you're wondering, if y of 0 equals 0 is obviously going to give us the trivial solution of y equals 0. Forgot to mention that. But this eliminates that possibility. So let's try that again. If we plug in our initial condition, we get minus 1 plus, and then let's factor out s of s plus 1 equals 0. So if we can bring this 1 over to the other side, so add 1 to both sides, and then divide by s plus 1, we get y of s equal to 1 over s. Now, what we do from here is we take the inverse Laplace transform of both. So we just take a inverse Laplace. Right? But what do we know about this? Well, we know we defined y of s to be the Laplace transform of y, so the inverse Laplace transform of this is just going to be y. And if we recall from our previous work with the Laplace transform, the definition of the Laplace transform of e to the minus, no, as is e to the at is equal to 1 over sa. So this allows us to extrapolate that the inverse Laplace transform of this is something to the effect of e to the minus 1, s minus 1, so e to the minus, in this case not x, t doesn't matter, e to the minus x. And this, in fact, that's the solution for our case. Now you notice we're missing a c1 here. That's because we have our initial condition right here. And just as a sanity check, e to the minus x, the derivative of which is minus e to the minus x, that works. And obviously if we plug in 0, yeah, that satisfies the initial condition. So that is our solution, big check mark for us. So now that motivates another question, which is, what is the Laplace transform of a general function? Is there a nice closed form, or at least is there a nice form for that? So a good way to come up with a conjecture for the form is to just take the Laplace transform of the second derivative. Now I'll be moving a little bit faster, just because we've done this before, so I'll be omitting any use of t. And of course, note that we've defined the Laplace transform of f as big F of s. And we already know that the Laplace transform of f prime is equal to minus f naught plus is a little small. Just cut off our little f prime here. F prime plus sf. Cool. So let's find what the Laplace transform of the second derivative is. So let's plug in the definition really quickly. We get the integral second derivative e to the minus dt. Now we break this up by parts. We're going to get something to the effect of e to the minus t f prime, again, of t evaluated for infinity, plus s integral of f prime s dt. Right, so you can evaluate this, you can check this for yourself to ensure that it's correct. I just did integration by parts a singular time. So what are we going to get? Again, from this side, we're going to get, well, we plug in infinity, we get 0, minus, we plug in 0, this goes to 1, but this goes to f prime of 0, so we get minus f prime of 0, plus s times now, this is the Laplace transform of f prime, as you can see it's in that form, so plus s times the Laplace transform of f prime, so we're going to get plus s, well, it's unfortunate that I wrote a plus there, because it's actually minus for the specific value, so minus s times f plus s squared now f, which again you can verify for yourself, we just multiplied by s, positive s. So yeah, there we go, we're done. We know the Laplace transform of the second derivative. But the question is, can we come up with a general form for the nth derivative? And I say yes, of course. We can do some pattern recognition. We're good at that. And let's say that the nth Laplace transform of the nth derivative, I'll write the t one time, is going to be equal to, and it's going to be quite big, so I'll write it down here. I think we're going to have something of this form right here, so not the highest derivative, but one less. And I think they're all always going to be of the 0th position, and they're all going to be negative. So let's start with minus f n minus 1th derivative at 0. And then I think it's going to go down by 1, which would mean the next one is minus f n minus 2 derivative at 0. But I also think it's going to gain an s each time, because you can see that, this f gained an s, and then this f and this f gained an s. So I feel like each time it's going to gain an s. So that's probably going to be s over here, and the next one's probably going to be s squared, f to the n minus 3 derivative at 0, right, and so on. And then I think if we continue on over here, since we have, n different terms here, right, because on the second derivative we have 2 different initial condition terms, the first derivative we have 1 initial condition term, we're probably going to have n initial condition terms, and this goes down by 1 for each term. So on the nth term it's going to be n minus n, which is just 0, and the 0th derivative is just f. But this goes up, not by 1, it does go up by 1, but it starts at s to the 0, right? Because this is s to the 0, s to the 1, s to the 2. So, but this is the third term, so on the nth term it's probably going to be s to the n minus 1 at 0 over here. And then, of course, we're still going to have this term right here, plus f of s, the long plus s. But it gains a factor of s each time. So no derivative, s to the 0, first derivative, s to the 1, second derivative, s to the 2. So this is probably going to be s to the n, right? Now this is not a theorem or proof, this is conjecture. It's conjecture based on pattern recognition. And it is correct. But we have to show that it's correct if we want to be comfortable in that fact that it's correct. If you would like, you can just accept this. But there's a very simple way to show this, and it's by induction. And to show it by induction, we do the following. We have to show 2 things. First of all, we have to show a base case. And then we have to show that the nth case implies the next case. And the way you can think of this is that we have some dominoes. And we have n dominoes here. And then we add another one. This is the n plus 1. So what I want to say is, if this is domino 1, if I show that domino 1 knocks down domino 2, and then I show that for whichever domino we're at, the previous one knocks over the next one, then I can say that, okay, based on the fact that the previous one knocks over the next one, we know that 1 must knock over 2, must knock over 3, blah, 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 all the way down to n, right? So if we do these 2 things, the base case, 1, and the implication that the nth case implies the n plus 1th case, then we're done. We've proved it by induction. And something like this, where we have an nth derivative, is the perfect candidate for induction. So we'll in fact try it. And we've actually already shown the base case. In fact, we've done the base case overkill because we have 1, 2, 3 base cases. Well, you maybe don't want to count this, although you can. We have 3 base cases. So we've done that in excess. So let's just show it inductively. And the way the inductive proof works is once you show the base case, so for example, n equals 0, n equals 1, doesn't matter which one, you then assume, you begin with the assumption that the nth case is true. It's true. So what that means is we assume this, right here. Let's assume this. And then we show the n plus 1th case is true. Only based off of the nth case, and if applicable, our base cases, but they may not be necessary. Right, so let's assume that the nth case is true, and let's try to find what the Laplace transform of the n plus 1th derivative. Now we know what to expect. We do know what to expect. We should expect an additional, so let's see, n plus 1. We should expect an additional minus f nth derivative 0, and then all of these gain a factor of s as well. This goes up to n plus 1. All of these gain a factor, and that's it. That's what we would expect. What is this equal to? This is going to be equal to the integral of f n plus 1th derivative, e to the minus st, dt. Well, we can do the same thing we did on top with the product rule, or the integration by parts. That's the inverse product rule. And we can go ahead and take e to the minus st, f of n now. And my apologies, I didn't plug in the bound, or I didn't write down the bound. Infinity 0. Minus integral of 0 to infinity of f of now 1 less, because we took integral f of n, e to the minus st, dt. And remember, we took the derivative of this, so we get a factor of minus s. This minus becomes a plus, this becomes an s. Well, what do we get from here? Plug in infinity, quote, quote, plug in infinity, you get 0, and then we do minus plug in 0. This goes to 1, this goes to minus f of 0, plus s times, well, what is this? This is just right here. This is the nth derivative, this is the Laplace transform of the nth derivative, plus s times the Laplace transform of the nth derivative. Well, are we done? Let's see, what did we predict? It should have been based on our conjecture. It should have been that we would gain a case for one higher derivative, so minus f to the nth derivative of 0. And everything else that's in this formula currently should have stayed, just gained a factor of s. Well, what do we get? We got that additional term, minus f to the nth derivative of 0, plus the exact thing we had before, just everything gains a factor of s. Yep, that's done. We say the induction is closed.